If I asked you for the simplest example of an irrational number, you would probably say square root of 2. I have also always thought that the square root of 2 is the simplest irrational number, meaning that it's easiest to prove that it's irrational. But to my great surprise, I have recently discovered that it's even easier to show that log base 2 of 3 is irrational. And that's what I would like to share with you in this video. But first, let's put our discussion in the proper perspective. Let's look at it historically. The fact that the square root of 2 was irrational was known to the Pythagoreans in the 500s BC. So it's been known for a very long time. Now, if you're watching this video, you're probably familiar with the standard way of proving that square root of 2 is irrational. Now, that proof is based on an argument that, in my opinion, is more than a little subtle. And I remember that it took me quite a long time, possibly years, to get used to that proof and accept it to a degree. But in any case, the same argument can be used to show that the square root of any number that's not a perfect square is irrational. And similarly, the cubic root of any number that's not a perfect cube is irrational. And so on for all powers. So that's it for simple powers. What other numbers do we know to be irrational? Well, it turns out that we know the two of the most important numbers in mathematics to be irrational as well. Euler, the great Leonard Euler, proved that E is irrational in 1737, so more than 2,000 years after Pythagoras. Now, to be fair, the number E was only invented about 2,000 years after Pythagoras, but in any way, these things take a very long time. And the proof of the fact that E is irrational is very complicated. Of course, the very definition of E is quite complicated because it invariably involves an infinite process. So if you want to prove that E is irrational, you have to use the definition of E. And so, unavoidably, you will have to use calculus in order to show that E is irrational. And that's very difficult to do. If you were to pause the video right now and try to prove that it's irrational, you will probably not be able to do it too quickly. Well, Euler did it in 1737, and my guess is that he didn't actually set out to prove that it's irrational. He was studying the properties of the number E, and he realized, looking at all the arguments he had, that he was able to conclude that E is irrational. It's a very beautiful proof, and we'll discuss it soon. Now, I'm sure that Euler was very curious to know whether pi is irrational. And I think that everybody always suspected that pi is irrational. But it wasn't Euler who proved it. Interestingly enough, it was a friend of Euler's, another Swiss mathematician, Johann Lambert, who proved it 24 years later in 1761. And that's an altogether different proof. So what we learn from this is that every number, or every kind of number, requires its own approach to show irrationality. And all of those proofs are quite complicated. So when you encounter a new number and you want to prove that it's irrational, you're up for an uphill climb at the very least. So I have always assumed that because log base 2 of 3 is not obviously irrational, that it would be quite difficult to prove that it's irrational. Well, actually the opposite is true. It's almost obvious that log base 2 of 3 is irrational. And that was a great surprise to me. And here's that very simple proof, which I actually think you will be able to come up with rather easily if you were to pause the video and give it a shot. But in any case, here it is. So the same argument can apply to log any base of any number. But I'll save that for you as one of my challenges. Let's just show it for the specific example of log base 2 of 3. Let's assume that it's rational. And so it can be written as a ratio of two integers. And now let's ask ourselves the question, what does this mean that log base 2 of 3 equals m over n? Well, by the very definition of the logarithm, this is a number such that if you raise 2 to that power, you get 3. That's what log is. So 2 to the power m over n must equal 3. Let's write this down. 2 to the power m over n must equal 3. And now, to get rid of a fraction on the left-hand side, let's raise both sides to the power n. And so on the right-hand side, we'll have 3 to the n, and on the left-hand side, we will simply have 2 to the m. And right there, we have reached a contradiction, because the number on the left is even, and the number on the right is odd, which is not possible. We have reached a contradiction, and therefore, log base 2 of 3 cannot be represented as a fraction of two integers. So how simple was that? I don't think that any proof of irrationality can be simpler than that. What a great surprise. So that wraps up this proof, and let me leave you with two challenges. First, as I mentioned, with regard to a more general log with a general base of any number, two integers, fractions will not be much different from integers. So for two integers, come up with a criterion that will tell us whether this logarithm is rational or not. And for that, you will probably have to appeal to the fundamental theorem of arithmetic, which states that any integer can only be represented as a product of primes in a unique way. So if we use that argument for the example that we already considered, we would say that here we have one number that is represented as prime factors, 2 and 3 are prime, in two different ways. 2 to the m is one way, 3 to the n is another, which is a contradiction by appealing to the fundamental theorem of arithmetic. So that's what you would have to do here. So that's your challenge number 1. Challenge number 2 is a little bit more interesting. I have recently posted a video with a question of whether an irrational number to an irrational power can be rational. Whether an irrational number to an irrational power can be rational. And there are several ways to answer that question. The solution that I presented was absolutely beautiful. It only involved square roots of 2. And if you haven't seen that solution yet, I invite you to try and come up with a solution, answer to the question, which is yes, by the way, but you have to give an example, that only involves square root of 2. That solution is ingenious and requires a lot of creativity. Now, there could have been another way to conclude that the answer is yes, simply by saying e to the power of natural log of 2. This exponent, of course, equals 2 by the definition of log. And because e is irrational and log base 2 is irrational, this is the example that proves that an irrational number to an irrational power can be rational. But this, of course, is cheating in the context of that problem, because the proof needs to be from the basic principles. And if you use this as your example, you would need to prove that e is irrational for that answer to be satisfactory, and that log of 2 is irrational. But as we mentioned, it's not at all easy to show that e is irrational. It was Euler who first showed that e was irrational. And even once you prove that e is irrational, it's not entirely straightforward to show that natural log of 2 is irrational. So while this is correct, and does help us conclude that an irrational number to an irrational power can be rational, it's not valid. So my challenge to you is to use these logs, these numbers like this, to come up with an example of an irrational number to an irrational power, and now we know more irrational numbers, can be a rational number.